Hi. I'd like to talk about global warming in perspective of Venus and Earth. I frequently hear the argument that Venus is and try to either dispel a flawed argument or try to make an argument that hasn't really been made convincing, turn it into a convincing argument. So what I'm going to start out by is just showing you this data that Venus is 735 Kelvin. It's a distance of 108.2 million kilometers from the Sun, while Earth is about 50% further. They have these levels of carbon dioxide and nitrogen. Earth has a lot of extra materials, oxygen, argon, H2O. I'm not going to get into that makeup for a while. I'm just going to mostly be using what's called Stefan Boltzmann's equation. And Stefan Boltzmann's law goes power divided by area is sigma epsilon T to the fourth, temperature to the fourth. P is the power. It's measured in watts. A is area. Area is usually 4 pi times r squared. This is the area of it, the surface area of a sphere. Sigma, this is the Greek letter sigma, and it's used to represent the Stefan Boltzmann's constant. You can see derivations of this thing on Wikipedia. But anyway, it's 5.67 times 10 to the negative 8th watts per meter. Watts per square meter per Kelvin to the fourth. So that just is basically those units there are designed to turn what's over here into watts per square meter. So I've set this problem up myself. These problems I'm about to do, I've set them up myself. I'm going to work out the answers to the best of my current ability, and I strongly suspect that there are large conceptual errors in this. So I'll try to highlight any claims that I find dubious, and I hope to encourage people with better ideas of how to approach these questions to reply. Now, the Sun is considered to be an almost perfect blackbody. It reflects no light off its surface, so its albedo equals 0. This is generally kind of a surprising concept to people. It absorbs all the incident light on its surface. All of the light that it is producing is coming from thermal energy. So its emissivity is 1, and its surface temperature is 5778 Kelvin, and its radius is 696 times 10 to the 6th meters. We're going to use Stefan Boltzmann's law here. Power equals area times epsilon, or sigma epsilon T to the fourth here. Can plug that into our calculator, and we get 3.85 times 10 to the 26th watts. Pretty powerful. Question 2. The Earth is not a black body because it reflects much of the light incident on its surface. The Earth's average temperature is 287.2 Kelvin. Its albedo is 0.37. Its radius is 6,371 kilometers. I want to use Stefan Boltzmann's law again to figure out the thermal energy. Actually, it should be the thermal power radiated from the Earth in watts. So this is actually power in watts. Energy per second is what it should say. Okay, let's see if I've made any errors here. Yes, I have, because this is supposed to be the area of the Earth's surface, and I forgot to square it. Okay, so this is better. The area is 4 pi times the radius squared times sigma. Sigma is not there. I need to put that in there. Okay, this is better. Now I've got sigma in there, 5.67 times 10 to the negative 8th. I've got epsilon, the emissivity of the Earth, which I believe is just 1 minus its albedo, and then the temperature, which is 287.2 Kelvin to the fourth power. So I think I've got all the terms in there now, and we get that the Earth's total thermal power radiated should be about 1.24 times 10 to the 17th watts. Now Venus, on the other hand, has a radius of 6,052 kilometers, so that's 6,052 times 10 to the third meters. Still got the Boltzmann constant, 5.67 times 10 to the negative 8th. We've got an emissivity of 1 minus its albedo of 0.67, and we've got a temperature of 735 Kelvin. Now, I mentioned earlier that I was going to make note of things that I wasn't quite certain of. I am using this formula that emissivity is equal to 1 minus the albedo. I'm not absolutely 100% confident of that. That might be a much more complicated calculation that we would need to do to figure out, because I think that albedo is based on the wavelengths of the light that are coming in or out, and using the same albedo for infrared spectrum as using the albedo for visible light spectrum may be a mistake. Also, at this particular moment, I cannot quite recall the justification for claiming that emissivity should be 1 minus the albedo. That the Stefan Boltzmann Law for I can't remember exactly why the amount emitted is such a precise function of the amount absorbed. But in any case, we have a value of 2.5 times 10 to the 18th. Let's get these both in the same order of magnitude. So this is, I'll just change this one to 0.124 times 10 to the 18th watts. And then you can kind of get a comparison of 2.5 versus 0.124, or you could call this 2500 versus 124. So Venus is getting significantly more power emanated to it from the sun. No, I forgot what I'm doing. Venus is emitting a massive amount of thermal radiation because of its 735 Kelvin temperature. Way more. Many orders of magnitude more. Many orders of magnitude more. What am I talking about? It's 20.3 times as much power is emanated by Venus, thermal radiation emanated by Venus versus Earth. So just to write that on the screen, Venus emanates 20.3 times as much thermal radiation as the Earth does. Okay, third question. The sun generates a power output of 3.85 times 10 to the 26 watts, which we calculated earlier. A portion of this energy lands on the Earth's surface with its radius of 6,371 kilometers, and it's 149.6 million kilometers away. And a portion lands on Venus at 108.2 million kilometers away, and I didn't give its radius. So, but I'll just go ahead and add that in there. Venus radius is 6,051.8 kilometers. Now, how are we going to do this? We're going to find basically, well, I'm going to use a spreadsheet to do this calculation. The power emitted in both cases is 3.85 E26. That's how much the sun emanates. We're going to do Earth's distance is 149.6 times 10 to the 9th, 149.6 billion meters. Notice this is in million kilometers is a billion meters. And Venus's distance is only 108.2 billion meters. Now the intensity is going to be the power emitted divided by the area made up by that a sphere of that distance. So I'm using cell B2 divided by 4 pi times C2 squared, which gives us the intensity of 1,370. Now I'm just going to copy that down because I can make the spreadsheet do the work for me. It tells me that the intensity at Venus is 2616.96 watts per meter squared. I'm going to go ahead and insert a column here, and for planetary radius, plugging in Earth's radius of 6,371 kilometers, which is 6.3 times 10 to the 6 meters, and Venus at 6,051, which is 6.05 times 10 to the 6 meters. And for this surface area, we're just using a cross-sectional area instead of a surface area. So we're just going to take this as pi times the planetary radius squared. And the total power absorbed is going to be that intensity times the area. Actually, I should probably include the albedo in this calculation too, shouldn't I? So let's call this the power incident. Go ahead and plug in their albedos of 0.37 and 0.67 respectively, and then the power absorbed is going to be the power incident times 1 minus the albedo, the amount that's reflected. So that'll be the amount of power absorbed by the sun. We'll have 1.1 times 10 to the 17th and 9.9 times 10 to the 16th. Now this seems rather amazing, that the Earth absorbs more power from the sun, according to this calculation, than Venus does. Venus reflects most of that power, even though there's 3 times 10 to the 17th incident. If this albedo calculation is correct, then it's actually absorbing less energy from the sun than the Earth. Just slightly less, but less. No, anyway. Now, question 4 asks us to compare the amount of radiant energy incident on the Earth versus thermal energy emanated on the Earth, and do the same thing for Venus. I'm going to go ahead and actually add an extra column to this, since you notice I've got power incident and absorbed up here. And earlier I calculated these values for the amount emitted. The thermal radiation emitted by Earth was 0.124 times 10 to the 18th. By Venus was 2.5 times 10 to the 18th. I'm just going to leave the times 10 to the 18th out of these and just do so that it'll fit. This incident power is going to be 0.175 times 0.175 times 10 to the 18th. This is going to be 0.301 times 10 to the 18th. The power actually absorbed from the sun is 0.110 and 0.094 times 10 to the 18th watts. Now, the way I've done this calculation, there is a huge flaw. I can tell because the amount of energy absorbed and the amount of energy emitted should be pretty close to the same value, unless there's a massive inner reaction going on in the core of these planets or something like that. Most of the energy coming off of the surface of the planet has to be coming from the sun. Actually, no. Earth, now that I look at it again, let me look at this again. Incident on the Earth, 0.175. Absorbed, 0.110. Emitted, 0.124. These are actually pretty close, the 0.124 and the 0.110. With Venus, though, you've got a really massive difference between the amount of incident radiation coming from the sun, which is 0.301, and the amount emitted, which is 2.5 times 10 to the 18th, which is 2.5. And this seems like something kind of curious to me, as though Venus, is this the greenhouse gas? Is this really a greenhouse effect, or is there something bigger and more major going on? Like, my suggestion would be that Venus has had a recent collision with an extremely large asteroid or moon or something along those lines. Or maybe even a great thermonuclear war between its previous inhabitants that has caused massive devastation to the planet. Probably more likely to be just an asteroid. Now, I had written a couple of other questions here, but I was going to use another application for Stefan Boltzmann's equation I often see used, which is to find the radiant temperature based on the intensity of light from the sun and compare. So basically I was going to do the calculation where given these intensities of the light at that point in space, do some calculation using Stefan Boltzmann's equation and solve for T to find the temperature of that point in space. My general question was, is that temperature of the vacuum of space through which radiant energy is passing, is that a valid concept? Is the temperature of space, does that really make any sense? Should the second law of thermodynamics apply in that sort of situation? Will heat spontaneously flow from that point in space which you determine its temperature via the Stefan Boltzmann Law? Does that temperature apply to the second law of thermodynamics, where heat will not spontaneously flow from a cooler body to a hotter body? Well, I kind of think that maybe heat will flow based on the fact that that you've got that high intensity, or you've got that high frequency radiation. It can still put energy into a hotter body. Well, and technically it comes from the sun, which is a hotter body. So, but radiation versus, or just kind of wanting to make some kind of distinction between radiation between bodies through a vacuum and conduction between bodies that are thermally connected by some physical substance. I still do want to answer the question, is carbon dioxide and the greenhouse effect a major explanation for Venus's extreme temperature? I am in doubt. Let me just say that this emission of 2.5 times 10 to the 18th watts versus an absorbed, an incident temperature of 0.094 times 10 to the 18th watts, it just seems like such an extraordinary difference that I can't believe that it is caused primarily by the greenhouse effect. The greenhouse effect seems like a much more subtle, like it can increase the temperature by maybe a couple of degrees, but not this massive thing that Venus has. Now, another question I had on my list was more of an essay question that I don't really necessarily know the answer to. The final question here is, how is infrared absorption energy converted into thermal energy? And I think that is kind of a fundamental question to global warming, something that needs to be explained in detail to really explain the history of why the scientists are doing all of these. Why did they have this suspicion that they needed to check the temperatures versus the carbon dioxide levels? And why did this study get started in the first place? What was their reason for believing this might be the case? How is infrared absorption energy converted into thermal energy? I think would be a good starting place for that question, and get away from the debate about global warming and start the education about global warming.